And at the peak of a contraction, the calcium concentration increases about 100-fold to 10 to the minus 5 micromolar. Okay, so that's a lot of calcium.
Are they both micromolar or are they both molar?
Oh, they're both molar. Sorry, I'm sorry, Toby. Take away the micro. There you go. Thanks. Otherwise, you'd be a whole lot smaller. Okay, so the pump, I'm trying to think of, I'm just going to erase and move forward, move from left to right. So the pump is kind of has a bulb that does the ATPase activity. And E1 looks kind of like this, okay? ATP is there present, waiting to be hydrolyzed. Okay, so we kind of have the pump primed for hydrolysis. Okay, the Km for the calcium is 10 to the minus 7 molar. Okay, so is this pump operating when the cell is at rest? Look at the Km, look at look at this. It's 50%. It's operating at 50% its maximum velocity. So yes, it is operating, but only at half of its maximum velocity. Okay, how about up here when we now have 100 times more calcium? You're probably working at or darn close to maximum velocity, okay? So the Km is it's interesting that the Km is situated just right, or at least maybe this concentration is created because of the Km of the sodium, of the calcium ATPase. Okay, so particularly at the end of a muscle contraction when the calcium is kind of high, calcium is going to bind, okay? Almost as soon as the sites become available. And this is going to stimulate, the binding of calcium stimulates the ATPase activity or the protein kinase activity. In transition. Okay. So the binding of calcium stimulates the protein kinase activity or the ATPase activity of the pump. The ADP is going to stay bound for a little while. We're sort of in transition, we're not in Q1. We're sort of kind of becoming close because we've got the protein phosphorylated. And then we do the flip, and I intentionally did not put the ADP back on because it doesn't stay there. Okay, I'm going to put this for right now so we can think about what's going to unload. on the sarcoplasmic reticulum side of the membrane, there are, what do you think the potassium, the Km of the potassium binding site, or calcium binding site is going to be? It's going to be a really high or really low? Really high, okay? And it is now 10 to the minus 4 mole, okay? So in other words, it's 1,000 times, it has 1,000 times less affinity for calcium in this configuration, in the E2 configuration, than in the E1 configuration. Okay, so what do you suppose that's going to do? Yeah, it's going to cause potassium to, or I keep saying potassium times C and the K. It causes the calcium to release, but hang on to your hats. It will release, but there's a but to that. It will release. ATPases all in here. And we're going to pop back into we're going to hydrolyze the PO. I'm going to remove the phosphate. Okay, we're going to pop back. We're going to reload the ATP so that this pump is ready to do another run. And if this is at the end of the contraction, immediately those calcium binding sites will be occupied and we'll do a cycle, another cycle. Okay, so here is the but. You got that? Okay, here is the but. Inside the ER, or SR, the calcium concentration is somewhere between 2 and 5 times 10 to the 4th molar. Okay? Is the calcium going to be unloaded?
According to that,
No, it's just like what? The calcium concentration is significantly higher than the Km, and yet the calcium does come on. Okay? This is a tremendously concentrated sac of calcium. So the question then is, how in the world can you unload that calcium if the calcium concentration is so high? Okay? Well, the answer is we'll disguise the calcium. So that, in other words, what we're going to do is move the calcium someplace else as it becomes unloaded. Okay? So we'll unload the calcium here. And one way to reduce the amount of free calcium in the sarcoplasmic reticulum is to have a bunch of proteins that can mop up the calcium. Okay, so there is a protein in the endoplasmic or in the sarcoplasmic reticulum called calsequestrin. Can you read it? And calsequestrin has a capacity to hold a lot of calcium. So we sort of disguise the calcium by mopping it up and binding it to calsequestrin. When the calcium channel opens and calcium starts to come out, that just suddenly shifts the equilibrium and calsequestrin unloads its calcium. Okay, so it takes a lot to get that calcium, it actually does take a lot to get the calcium to get into the sarcoplasmic reticulum, and the cell always has a trick to do what seems to be impossible. Okay, what kind of amino acids do you think are, would you find in calsequestrin? Lot of very negative amino acids. Aspartate, glutamate, histidine, or is that positive?
It's positive.
It's positive. I can never get histidine. That and tryptophan are two bad, the ones I can't do. Okay. So I think that takes care of it. Is there anything? Okay, got 10 minutes for something weird. Okay. Unless there's questions. Okay, so a little bit of weird stuff. Okay, we're going to be in the mitochondria for a minute. Here's the electron transport. Okay, and here is, this is inside the mitochondria, that's in the matrix, even inside the inner membrane. Here's the intermembrane space. Okay, and you'll remember that the electron transport system, I'm just going to put you always usually do this here. The main job of the electron transport system is to convert the energy that was stored in the electrons into a proton gradient. And then the proton gradient allows the protons to go back through ATP synthase and make ATP. Okay, but we almost always think of that all of the protons that got pumped out of by the electron transport chain are going to be used for ATP synthesis, and they're not. Okay, that proton pump, that proton gradient has other usefulnesses besides that, and I'm going to get to the funky thing in a bit. For example, I'm going to get this wrong, my picture's upside down on the board. So, this. Okay, so once the ATP is made, okay, there is a transporter that will move that ATP out of the matrix in exchange for ADP. Okay, so we get rid of the charged ATP. Okay, that's done. Let's get it out of here. Let's bring in some ADP so we can make more ATP. Okay, but we have to bring in the inorganic phosphate. And there's more than one way, but one of the ways is, oops. To use the proton gradient to pump the inorganic phosphate into the inner mitochondrial matrix. So that now we have both ADP in the matrix and we have inorganic phosphate in the matrix. Okay, so that particular, those protons are not available for the ATP synthase. Okay, so we're not going to get, so not always is the, in fact, even though most of the time the protons are flowing through ATP synthase, they're not always flowing through ATP synthase. There's also another one that the cell uses sometimes. Sometimes pyruvate. There's more than one way to get pyruvate into the mitochondria, so it can, what's pyruvate converted into? Yeah, acetyl-CoA, and that happens in the matrix. But one of the ways, I said there are multiple ways, is to move pyruvate in with protons moving down the concentration gradient. So again, those are protons not used for ATP synthesis. So there was, did we talk about this in Bio 111? There was at one time somebody thought, oh, wouldn't it be nice if we could figure out a great weight loss drug? Because there really hasn't been any good ones on the market ever. This one would be also, would be classified as probably not a good idea. Dinitrophenol. Have you talked about this one? Huh? You may have used it. We use it too. We used to use it in, I can't remember what. It was used, sometimes it's a beta-galactosidase. A beta-galactosidase substrate, you can attach it to galactose. I think it's yellowish in color. Okay. Okay, here's the reaction. This is what's going to happen if someone takes dinitrophenol. There's dinitrophenol, and then this would be okay. If it picks up a hydrogen ion, and it's likely to do that at high concentrations of protons, like in the intermembrane space, the protons can get almost pushed down, and we get a hydrogen. Well, this is soluble across the membrane. And it'll diffuse into the, let's say the matrix, the inside of the mitochondria, where the concentration of protons is fairly low. Okay, so this is intermembrane space, And the concentration of protons in the intermembrane space is fairly low, so that favors the unloading. And so there's a flipping back and forth. So dinitrophenol carries hydrogen ions from a high concentration to a low concentration. So when nitrophenol is present, the protons have a couple of ways to go back into the matrix. They can ride the ATP synthase and make ATP, or they can write this way, and what's going to happen to the energy released? No ATP is synthesized, but what happens to the energy that's going to be released?
Just gives off as heat.
It's going to be released as heat because you're not doing, it's not doing work. Still, the energy is being released, but if it's not being used to do work, released as heat. How would this? So, if you're in the presence of dinitrophenol, what's happening to the amount of ATP synthesized? It goes way down. So you eat something that has a lot of glucose, something starchy, you got a lot of glucose. So instead of getting 30 ATP out of glucose, you're going to get a lot less. Okay? So that means you got to burn a whole lot more glucose to get this the same amount of ATP. So that's how it's thought, oh, this is a great diet drug because you can eat, but you're not going to turn that food into ATP. You're essentially wasting the energy. But you're wasting the energy released anyway in the form of heat. And wouldn't you love to sit next to somebody who has eaten a lot of dinitrophenol? Can you imagine the heat that had to be eliminated from their bodies? Turned out not to be such a hot idea. Huh? You probably generate too much heat, which could be in itself kind of dangerous, but I could just say, it's too hot. But anyway, but we talked about, we have red fat or brown fat back at the tuft of our necks or at the base of our necks, which uncouples. It has a protein that allows the protons down the concentration gradient. I don't want to call it a channel, but a protein that carries the protons down the concentration gradient so that they don't go through the ATPase or the ATP synthase. And I'll say more about that tomorrow. I'll say a little bit more. So I'll have to tell you about our friend from Champaign, Urbana, who could out-eat anybody. So remind me to talk about Bob, the big eater. Bob, the big eater.